They should have said the poet. The poet. They should have said the poet. The poet.
Sending poets.
This is Sending Poets, a podcast about ideas. Our goal is to understand metaphorical truths within the beauty we find in the human experience. My name is John. With me is Bob and Tucker. What's up, fellas?
Morning,
guys.
And we're continuing three-body problem convos. This time we're going to focus on the solution side of things. So there's going to be several thought experiments. I wanted to make this quick disclaimer. If you happen to be driving while you're listening to this, either pause when those come up, or just make a point to come back to it, because it's really encourage you to try to get into this like meditative experience where you can really focus on these thought experiments. Should be awesome. You can email us your thanks later, sendingposts@gmail.com when you enjoy these things. So anyway, Bob, a lot of these things are in the solutions, are kind of these ideas you've had for a while. So I think I'm just going to turn it right over to you.
Thanks, John. Let's just put this in the realm of daydreams. I think that's where we want to be with it, meaning intense daydreaming. You're trying to visualize in your own way. So the words are very important, but it's almost as a guided meditation. You want to fall into your own daydream and visualize these things. And I think the very, very first point to visualize is this concept of dimensionality. And specifically from a very famous book called Flatland. And this was written, I think, in the 1800s by a gentleman, his name is Abbott, Edwin Abbott. He is somebody that probably none of us are familiar with, but maybe a handful have picked up this little book or seen a video on it, Flatland, and it's discussing what it's like at different dimensional levels. So just real quick, as a dimensional point of view, I think it's important to put your mind in the point of view of the dimension itself. And let me give you an example. So Tucker, if you're a piece of string, you're literally a section of string. All it is length. And you are a given length, let's just say 1 meter in the string, and you're moving up and down a longer string. You're a part of the string. You're inside the string. You are the string. And you come across another piece of string coming at you on the same length of string. When you look at the other piece that is a length of string, what does that look like to you?
Would be a dot.
Exactly. So you have length, but your length end on to another piece of length looks like a 0 point, so a non-dimensional dot. And obviously we can expand this. So if you are on a sheet of paper, two-dimensional now, you have length and width. And let's say instead of a length of string, you're a circle on the paper, and you were to visualize from within the paper, not above it, not below it, but from within the paper, you're a circle and you encounter another circle. What does that other circle look like to you?
Now we have a line.
So this is what we see as a pattern. Exactly. We're losing one level of dimensionality. Let's make it even clearer with one more illustration. Let's go to 3 dimensions. So without two eyes and without parallax and using the ability to have stereoscopic vision, if you are a sphere and you look at another sphere, what would that sphere appear to you?
circle.
So we can see the pattern here. The pattern is we always lose one level of direction or dimensionality in the transmission of the signal itself. So a line that has length looks to another piece of line as a point. A circle that has length and width looks as a line, which just has length, to another circle. And then a sphere, which has length, width, and height, looks as a circle without, obviously, two eyes and stereoscopic vision. So having that ability to understand that being the object itself, you're going to have a point of view. Whereas if you're looking from above, objectively down upon the string, down upon the circle, down upon the sphere, we would see things differently and would be easily aware or transparent to us from an objective point of view. But it's hit to the subjective point of view of the entity in that dimensionality. And I'd like to bring up the first thought experiment here. So imagine you're in a room, and it's a very small room, just a cube with a desk on it and a chair. And you sit down at this desk and you see on the desk a piece of string and a pair of scissors. If you were to cut that piece of string, Tucker, how many pieces of string would you have?
2.
Okay, now imagine this room. The only difference is there's a PVC pipe coming out of your left-hand side of the wall and a PVC pipe coming out of the right-hand side. And they end right at the edge of the desk. And there's a string that goes out of the left side into the right side or vice versa. And you have a pair of scissors on that table as well. And if you were to cut that piece of string, how many pieces of string would you have?
So there's string hanging out of both sides of this PVC.
It comes from one side, pick your choice. It doesn't matter, there's no original side, but it comes out of one side and into the other, and it crosses across your desk.
So it's a connected, like it looks like it's the, just to chime in here, like it's not like two ends are coming out. It's a continuous piece going from one PVC pipe through into the next PVC pipe.
Precisely, with the opening exposed on your desk and your ability to cut it in that exposed area.
Well, immediately I would think you would still have one piece of string because my mind would say those are connected, but in reality you could have 2.
Okay, that's well played. I think that's a correct assessment. Let's make it clear though. Let's say there's also a little bell on the desk. And for everybody else trying to visualize this, I think you're already there, Tucker. If you were to tie the little bell after you cut the string to, let's just say, the left-hand end of the string now, tie the little bell, and you were to take the right end of the string that's still coming out of the PVC pipe, if you were to start pulling on that string, that little bell, you would hear it tinkle as it's being pulled into the left-hand pipe. Tinkle, tinkle, tinkle as you're pulling the string. Then you would hear it fall. It would fall down and make a sound underneath the floorboard, so to speak. And then you'd pull for a little while and nothing would happen. And then all of a sudden you start hearing it tinkle, tinkle, tinkle as it's being pulled underneath your feet. Tinkle, 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 and then up the wall, behind the wall, obviously, as you're pulling on the right-hand side. And you would pull this string out with the bell still attached at the end.
Meaning I have one piece of string.
Exactly. So I think that is a well-played illustration. Now, let's go from a piece of string, and let's say the string is made of paper, and let's just say the edges are sticky, so that you can wind on a flat surface back and forth, up and down, next to each other, an infinite weaving of these pieces of string until you get not one dimension of length, but you have width as well. So you essentially can take a piece of string and line it next to each other many, many times, create a flat surface. Let's just call it a piece of paper. Would you agree?
Sure.
Okay. So now we have this piece of paper on the desk. So it's got length and it's got width. Now, if you were to take that pair of scissors and cut that piece of paper in half, how many pieces of paper would you have?
Oh, many, many. It would depend on how many layers of string it took to make that length and width.
Let's just say, fair enough, but let's just say that the paper is now, the string has now glued itself together such that it is equivalent to a standard 8.5 by 11 piece of notebook paper or whatever. So no games with the edges being, not exactly right or whatever. It's now effectively a piece of paper. We're just trying to go through the example that if you lay a string next to each other, you're creating width. So now you have a length and width of a piece of paper. If you were to cut that piece of paper in half, how many pieces would you have?
2.
Very good. So now imagine that piece of paper uncut. If we were to roll it, let's take 8.5 by 11. If we were to roll it such that it looks like the tube inside of a paper towel. So the long edge is, the cylinder. You're making an empty cylinder essentially. Okay.
Mm-hmm.
So visualize the tube inside of a paper towel roll. Now, if you were to cut that with the scissors in half, how many tubes would you have?
2.
Now, if you were to cut from one hole to the other hole, so lengthwise along the 11-inch section, not the 8.5 where it's rolled up, if you were to cut from hole to hole, up the middle, so to speak, cut it in half, but hole to hole, how many pieces of paper would you have?
You would have 2.
So
you'd have one, right?
You would have one. So imagine you have this.
Oh yeah, okay. So you're not cutting through both sides, but you're slicing
One side.
One side. Yeah.
It is technically cut in half because you're cutting the whole length, but you are cutting it up from one hole to the other. And then just imagine it's not cardboard. Just imagine it's paper and it just lays down flat again. So if you were to, okay, so now we're at 2. Excuse me, now we're at 1, meaning one piece of paper. So instead of cutting it and dividing it into 2 things, we can cut it and divide it into the 1. Essentially, it's undivided, okay? Now let's go with a tube, piece of paper that's rolled into a tube, but now we can connect the ends of the tube. So that looks like a donut, okay? And I ask you with the pair of scissors, cut that donut, transect a piece of that donut in half. How many pieces would you have?
If I'm visualizing this correctly, you would have 2. If you're
just one cut, not both sides. So just one cut of the but you're cutting like, remember when you cut the paper tube in half?
So we're cutting the outside edge, but leaving the inside.
Yes, but you're only cutting it once, meaning just like you did with the tube before where you cut it in 2, but now we've connected the edges. So the same kind of a cut. How many pieces would you have?
So now you're taking a 3-dimensional donut, you cut the outside edge, and it turns back into a 2-dimensional piece of paper.
Not quite. Now we're going to get there, but not quite. So you imagine you just have the paper towel tube, but you connect both ends to make the torus shape, the torus, the donut shape.
Mm-hmm.
Like if it was a clock, if it was standing up, it was a clock, and you'd cut it at like 12 o'clock.
Very good, but not all the way to 6. That's exactly right, John.
Right,
Very
just
good.
cut it at 12 o'clock, and then it kind of unfolds into the tube again.
Correct.
Yeah.
So
Yeah.
just
Yeah,
so
gotcha.
you still have so we're going to go through the whole thing backwards now in reverse. So imagine you have the donut, and we can fully cut it in half, but it doesn't become 2 things. It turns into a tube. But then if we cut the tube from hole to hole up the middle, it doesn't cut in half. It becomes a piece of paper. And then if you were to cut it one time through, but like following the lines, like where the string was put together side by side by side by side, you could cut that piece of paper back into one long string. And then if you cut it, then it becomes 2 things. So the point is, the dimensionality is not in the length or the width and the height. The dimensionality is in this looping effect, where if you cut something, it doesn't become 2 things. It stays as 1. But you can't do that without an added layer of dimensionality. So the string is length. But when you loop it around on itself, it travels through height or width. Pick your choose which way, every way you like. It still only has length. If you're inside the string, all you know is length. And if you come across another section of string coming at you, it looks like a point. But once you loop this thing, If you cut it, you're not cutting the string into two pieces. You're just cutting out a layer of dimensionality because the string is transiting through a second direction, let's call it height, but it doesn't lose any length. Is that clear?
Yeah.
Okay, so that is kind of an alternate way to consider dimensionality, aside from just length as a dimension, width as a dimension, height as a dimension. So I'm trying to get away from coining or coinciding dimensionality with a direction or a line of force, let's just call it. So that's one of the main points here is dimensionality is in the looping, not necessarily in the direction of travel. And I can make that more clear with what I call wave theory, a way to take let's just say a string and understand the mechanics of the wave such that a string has length. But if you propagate a wave along that string of length, the wave transits through another direction. Let's just call it height. So if you were to take a rope and you were to, have it one end tied to a wall, let's say, and you shake it up and down, you're going to propagate a wave, right, along that piece of string or that rope. Now, the rope has length, but if you do not have the ability to transit through height as well, there's no wave. So the components of the wave, let's just say, are the zero line, so flat wave, or no wave, just flat. Then there's a positive section, which is above the zero line, arbitrarily so. And there's a negative section, which is below the zero line. And you could flip those around. It's not like positive means more and negative means less. It's a coordinate. So positive is the coordinate above the zero. Negative is the coordinate below the zero. So if you propagate a wave along a string of length, that waveform transits in one dimension, meaning along length, but it uses positive and negative height to do so. Everybody follow?
Yep.
Yeah.
Okay. So the properties of a wave that I want to expound upon are things that we're very familiar with. Let's take you guys are musicians. Let's take a guitar string. And the first one is going to be, for each action, there's an equal opposite reaction. So for every action, and these are not my words, you guys have all heard this before, for every action is an equal and opposite reaction. So let's say you have a string on a guitar and you pick a place, middle of the string, and you pluck it. Does the vibration of the string only go one side?
No.
It goes
It
both sides.
vibrates back and forth
Yeah.
in a diminishing wave pattern.
Precisely. It vibrates back and forth. Does it go back and forth, Tucker, at one speed, let's say up, and a different speed down? Or are they opposite and equal speeds?
I believe it would be equal, but I'm not sure on the math on how this works. Because like I said, with a plucked string, it starts as a big wave and diminishes to a smaller wave over
And-
time.
Let's say
the
they're
place
I don't
you
know if
pluck
that's
it,
important.
That's a
well,
good
well,
point.
I think so, because it depends where you pluck it, right? In other words, like if you pluck the string in the very middle of it, then maybe that seems more equal.
Let me
But
qualify
you
it,
don't,
because I think that's
right?
a good point. Let me qualify it. Let's say the string is infinitely long. So the wave that's propagating, the string only has one tension. So the math is the waveform transits as a function of the tension of the string. So the more tension on the string, the faster the wave propagates, the higher the frequency. But
Okay. I think I understand what I'm trying to say now. So you pluck that string, it would transit back and forth at the same speed because that note never changes, just the volume, the
exactly,
amplicity, or what's the word I'm looking for?
amplitude.
The amplitude.
Yeah,
The
exactly
amplitude
right.
changes, the frequency does not.
Precisely. Very, very good. So, and let's just say it's an infinitely long guitar neck, let's just say. So we don't get the reflection back from the ends. We're not looking at that. That's not the point. But the point is, if you were to pluck the string from a zero position, so the string is, let's just say, at zero. And when you pluck it, it's now creating a waveform that transits to the positive side and the negative side, let's just say, of height.
Yep.
And that would be in equal and opposite directions. So waves will operate in equal and opposite directions. Number two, inertia. So an object at rest tends to stay at rest. An object in motion tends to stay in motion. So let's just say we propagate a wave from a string. But before we propagate that wave, it's just still. It's just flat. That string, unless anybody disagrees, will never self-propagate a wave out of nothing. So it's at rest. And from rest, it will remain at rest unless acted upon. And then once acted upon, it's going to propagate a waveform, and it's going to tend to continue. Now, obviously, we have the realities of, friction and I'm talking about like a hypothetical string now at this point, something in space where just because, because like in Earth's atmosphere, inertia doesn't hold true either. There's friction, air resistance, etc. But if you were to go to the moon and there's no atmosphere and conduct a test, things have more pure inertial properties in that once they're in motion, they stay in motion. And once at rest, they stay at rest. So we all agree that a string, if acted upon, will then propagate a waveform that will tend to stay in motion. And if we do not propagate any signal along that string, it will remain signalless. Is that agreed upon?
Yeah, roger that.
Last piece, and this comes back to your point, Tucker, about the dissipation of the signal, which is the universe tends towards entropy or disorder. And that's exactly right. So let's take another form of a string, but let's make it out of light. So let's say you have a flashlight, and let's just call the photons streaming out of the end of the flashlight like a big string. And let's say you are going to project that flashlight forward, and at 1 unit of distance, doesn't matter, let's just say that the flashlight covers 1 square on a wall, square of a given length and width. So given surface area of a square. Arbitrary, doesn't matter what it is. But let's just say after 1 unit of length, that flashlight illuminates 1 square.
Okay.
If we take another step in a unit, let's say that flashlight then, the beam of the flashlight, it's spreading its signal out, diminishing its strength, but covering a greater area. And let's say that next area is 4 squares. Then if you take another step out, the beam is diminished even further, the amplitude. So the light hitting every piece inside any square is lessened, but now the total area of that square is not 1, it's not 4, it's 9. So imagine 3 by 3 squares. Take one more step out. Now it would be 16, 4 by 4 squares. Take another step out. It's going to be 25, 5 by 5 squares. So let's just say, and this is the inverse square law, by the way. So 1 over 1 squared is 1. 1 over 2 squared is 1/4. 1 over 3 squared is 1/9. 1 over 4 squared is 1/16. 1 over 5 squared is 1/25. You can keep on going. But the point is, the wave disperses as a function of the inverse square, and it is akin to entropy in that the beam becomes more disordered, less powerful at any given point, but it reaches a wider and wider frame of reference, let's just say.
Wow.
So those would be 3 characterizations of a wave that follow 3 known intrinsic properties of equal and opposite. Object at rest tends to stay at rest. Object in motion tends to stay at motion. and the universe tends towards disorder or entropy as time moves forward. Another piece on dimensionality, and this goes to what we're here to talk about, which is the three-body problem. So one of the solutions in the three-body problem was to crack open or extract additional dimensionality from a single proton. So the Santee use their technology to focus energy at a single point, a single proton, let's say, and they're able to unwrap a hidden dimensionality that they call, hidden dimensionality. So we talked last time about higher dimensions and this lower dimensionality of tiny little dimensions rolled up. So Tucker was bringing up this concept of say fourth dimension is time. So fifth dimension, you get a better look higher up. Sixth dimension, higher up. Seventh dimension, higher up. Right, Tucker?
Yep.
For every time you stepped up, you can now look down upon and have more information and more knowledge of things in lower dimensionality to you, which is, one of the theories of dimensionality. The other one that the show used was cracking open lower dimensions that are tiny, tiny little rolled up dimensions. So imagine you've got a grid, looks like a grid of squares built by little tiny strings. And if you're looking straight down on top of it, it just looks like a grid of strings. One's going through width and the other one's going through, length. You don't see any height looking straight down on it. But if you were to look sideways on it, maybe you see that the string that's going through, say, the length portion is actually rolled up into little loops. So if you look down from above, the loop is hidden. You can visualize what I'm talking about. But if you look over to the edge, you look sideways, you see that there's actually a grid built by, strings, but they're looping. Does that make sense? You guys are familiar with
Yeah,
this?
almost like a log cabin, but it's like the same log. It just wraps around back and forth on top of each other, right? It's just kind of looping back. That's what you mean by looping, right?
Yeah, so like a literal a loop, but imagine the loop, it doesn't split. You can't see that the loop is edged next to it. So it looks literally like a single line if you look straight down upon it.
Right.
So imagine a Ferris wheel. And you're a bird's eye view from space. You're looking straight down on the Ferris wheel. What would the Ferris wheel look like to you?
Just a line.
Yeah.
Exactly. Once you get down at ground level, you can now see that the Ferris wheel is a big circle.
Okay,
But
gotcha. That kind of loop. Yeah.
Yeah, that kind of loop. You can't tell from
Not like a wall, but yeah, like a actual circle.
Correct, an actual
Yeah.
circle. But the transit of the circle is not obvious when you're looking from a certain angle. You have to look from another angle. So you have to interject width, essentially. So you have length and height. The height is hidden when you're looking straight down. But if you go over to the width side, or X, Y, and Z, whatever you want to call it, from the Z side, you can now see it's a circle. So one of the concepts used, obviously, like Tucker was saying, is higher dimensionality, where we have bigger and bigger views that we can look down upon. And the other one that the Santee use is lower dimensionality, these tiny, tiny rolled up dimensions. And there's a point to all this. The point is they are trying to satisfy 10 dimensions. 10 dimensions is very, very, very important in physics through string theory. So we're not going to get deep into this as an overview, but string theory mathematically requires 10, sometimes 11 dimensions in order for the math to work. But we have length, width, and height, and time. So current concept is we have 4 dimensions of space-time. So where do you get this extra dimensionality? It's either like Tucker was saying, you have to go up and up and up, or you have to go down and down and down. And so in string theory, the concept right now is, well, one of the concepts is these are tiny, tiny little rolled up dimensions that we are just oblivious to. But if you put into the equations the 10 dimensions, the math works. So let's just leave it at that at this point. But conceptually, I'm trying to look at dimensionality through a different lens. So next thought experiment, last one for dimensionality. Imagine blocks, like you would have blocks for a kid. It has an A on one side and on the other side a picture of an apple. B on the other side a picture of a banana. C on one side, picture of a cat on the other side. So everybody knows a cube, a little wooden block, right? So imagine you have these blocks you're playing with, and you form a little tiny wall, 2x2 wall. So you got 2 blocks on the bottom. Sitting on top of those 2 blocks are 2 more blocks. So you have 4 blocks. And if you look at it, it just looks like a 2x2 grid. But it has depth, right? Inside the block, there's something behind what you can see because you're playing with the blocks. So imagine where the blocks come together in the middle, there's an X formed. So can everybody see that X?
Yeah.
Okay.
Yeah.
So,
it's okay that I call it a plus, right? It looks like a plus sign.
Yeah,
Yeah.
definitely. It looks
X
like a
cross.
plus sign.
Yeah. Okay. Yeah.
Cross. Okay. So you have a block in the upper left-hand side, a block in the upper right-hand side, block in the lower left-hand side, block in the lower right-hand side. And we know that the block has depth. So you can go to the back side of the block and you can be at the front side of the block. Where the plus sign is, put yourself in the very back side of that block. So imagine you're facing it, you're an observer, but in your mind's eye, like crawl to the back side because you can't see the back side, it's obscured by the front side. And this is what happens with the loss of one layer dimensionality anytime you try to visualize something. But it's a block, so you can crawl back to the very back edge. Let's call that the 0 point. So in the middle of the plus sign, on the back edge of the block is the 0 point. Now imagine the block has length. So if you come from that 0 point back towards yourself, so from the back of the block to the front of the block, let's call that directional length. And if you want to say up is plus and down is minus as a coordinate, anything above the 0 line horizontally is positive height, and anything below that 0 line horizontally is negative height. And then let's say everything to the left of a vertical line of the plus is negative width. And everything to the right of that line, that vertical line, is positive width. So we just built coordinates. Doesn't mean that one has more dimension than the other. No more distance is on the negative width than there is on the positive width. The block just has a left-hand side and a right-hand side, so to speak, from the middle of the plus.
Mm-hmm.
Now take in your mind the concept of length is all positive. So from the 0 point to where you are as an observer, let's just call that positive length. So the back edge is 0 length and the front edge is positive length. So if you combine these directions, they're not dimensions in my opinion. Okay, length, width, and height is not a dimension, it's a direction. So you go from the back edge of the block towards yourself, every block has positive length. But you can graph these as having 4 areas of dimensionality, a function of the 3 types of directions. So the upper right-hand corner is going to be positive length, positive height, positive width. The lower right-hand corner is going to be positive length, negative height, positive width.
Mm-hmm.
The upper left-hand corner is positive length, positive height, negative width. And the lower left-hand corner is positive length, negative height, negative width. Is everybody on that?
Yeah.
Okay. Now imagine another set of 4 blocks identical to the first, but we're going to put them behind the blocks from your point of view. So you have the plus sign and the back edge is 0 for length. That's what we're calling it. So now add another 4 blocks, and those 4 blocks behind the original 4 blocks are all negative length.
Mm-hmm.
And you can play the exact same game we just did as a combination of length, width, and height. But now everything starts, instead of positive length, everything starts with negative length.
Yeah.
So I'm not going to go through it all, but you can imagine, you can recalculate this thing, changing only the length signal from positive to negative. It's exactly the same. Everybody got that?
Yeah.
Yep.
So now we have how many blocks?
8.
Okay, we have 8 blocks. But like with our current understanding of the 10 dimensions, it starts with length, width, height, and the 4th dimension is what?
Time.
Exactly. So we have space-time. So time is a dimension that is used for calculations for this purpose. So now imagine time is a twist along length. And imagine there's one twist coming from the 0 towards you along positive length, and another twist going opposite direction from the 0 point along negative length. So now if you count the twist going each direction from 0 along length, you would have 2 dimensions of time and 8 dimensions of space, which give us 10 dimensions.
Wait a second. By the way, again, if you're driving, like, what are you doing? Just pause it, pull over, like, close your eyes like I'm doing, like, get into
Yeah.
this, you guys. Anyway,
You can't do this while driving. It's very difficult.
but say that again. Okay, so the twist, can we just talk about the twist real quick? Is that like,
Yeah.
in my mind's eye, I was rotating the blocks like to the counter, like clockwise or something to get the twist? Is that the twist you're talking about, or are you talking about a different kind of twist?
A different kind of twist. So
Okay.
like imagine a long length is a piece of string. So when you twist the string, it does not transit through width or negative width or height or negative height. It's not a waveform. It's a spin. It's a twist. It is something that rotates on itself. So you don't need to have any more spatial dimensions to occupy a twist or a spin. And what I'm saying is, if we analogize time, it might be literal, but I'm just saying as an analogy, time is the twist, because I don't think anybody has to apply where does the space come in the 4 dimensions. Nobody has to point to where where does time come in the 4 dimensions of length, width, height, and time for space-time. Nobody points to say that's where time is. I'm just trying to give an analogy that the time could be conceived of as the twist of the string itself. So if it twists one direction, because this is about symmetry, guys. This is about equal and opposite. Okay, this is about, if I twist clockwise facing me, it's going to be counterclockwise going away from me. So what we have is the foundation, in my opinion, of satisfying 10 dimensionality without needing higher dimensions or lower dimensions. What I'm talking about is a graphical representation of all the dimensionality that exists in every place in space-time that we know of. I've broken it into quadrants, and then a mirror image of the quadrants. But you can imagine these things at all locations throughout all of space-time. So the point is, I've broken them into the quadrants so that you could visualize, hey, I'm a massive being. I have mass. Let's just say I'm constrained into positive length, positive height, positive width. So all I know, all I can experience is in the upper right-hand quadrant of the first wall of blocks that are facing you. So let's just say everything that we know of, because we're not able to transit as a waveform while we're massive beings. Mass cannot transit the waveform. So it does not oscillate. We don't oscillate through positive height and negative height. We have just positive height. We have positive length. We have positive width. We experience the upper right-hand block, and we have time. So we have these 4 known dimensions or areas of influence, whatever you want to call this thing, but it's constrained. It's constrained in the upper right-hand corner of this quadrant of the front side of blocks.
Say that last part again, please.
We as massive beings are constrained into not an oscillation on both sides of height and negative height, width and negative width, length and negative, positive length and negative length. We're constrained into the arbitrarily positive length, positive height, positive width. So like the upper right-hand block that faces the wall of blocks that faces you, I'm proposing we're constrained as physical massive beings in that one quadrant. But the reality is all the quadrants are collapsed upon each other, and they all exist in the same area of space-time. But we are, so electricity, magnetism, they transit. They go around all four quadrants. Things that are waveforms, they can go around all four quadrants. But things that are massive, but they're also two-dimensional. This is the key. A two-dimensional oscillation is able to go oscillating a long length, both positive height and negative height, or positive width and negative width. But what you cannot do is have a length by width by height waveform transit into the other quadrants. So mass is constrained. I wasn't going to go here, but let me give you an example. E equals mc squared. E equals mc squared. So energy equals mass times the speed of light squared. What if we solve for mass? Mass equals energy over the speed of light squared. What if the speed of light squared is two sets of waveforms, both along length, one oscillating between positive height and negative height, and one positive width and negative width, and they're bound around in a loop. If you were to cut that loop, you cannot destroy mass, you cannot destroy energy, you can convert one to the other. So if you cut the loop, it flattens itself out and it becomes energy. If you bind the loop, meaning bind a piece of energy around upon itself and create a loop, now you have mass. And the propagation of the signal, the waveform itself, is a function of the speed of light.
Dude, I have to say, just give me a moment here, because like I just need some time. I do have to say, I drank a beer last night called Brain Melter. Yo, did not hold a candle to the melting of my brain just from listening to you talk. So there's an endorsement.
By the way,
wow.
Don't drink and drive. Don't drink and drive, everybody.
Yeah, right. Yeah. Don't drink and drive, and don't drink and thought experiment with Bob. And the second thing, I love it. I don't know if you've been looking at I'm just curious, Bob. How long do you think you've been talking about this? Just curious.
Probably 30 minutes.
41 minutes.
All right.
It just you're in that zone where it's just like the time is just disappearing, man, because it's just the flowing and stuff. I was gonna say, like,
when you put it into imagination land, that's when time disappears, everybody.
Yeah.
You can get to the daydream. Why do you think people daydream? It's to pass the time away. It's a pleasurable thing, but that is the key, is this, not the words. It's putting the words into pictures in your mind and then rotating them around and looking at it, and then describing what you see. So if it's a time issue, we can cut it and make a two-parter, but I was going to say, because on one hand, I want to kind of apologize. I'm supposed to be trying to wrangle this into 90 minutes, and I'm looking at like, dude, like, it's not going to happen, man. I don't want to. I want to just be like, here. Do you want to just talk about dimensionality and just have some back and forth about this and not try to race through, or do you guys?
Yeah, let's talk about that, because we're like about halfway through, and you have 4 parts you've broken this into. So, we could keep stewing on this, and then maybe
two-parter. Let's do the first and the second, and we'll leave the third and the fourth. So the second is the Newtonian gravity.
Yeah, third, I'm good for that. If you're cool with that, Tucker. I mean, I know you like your brain is, I'm sure, just as melted as mine, and
So where we at? What do we want to talk about? The dimensionality. We have concepts, questions. Where are you at?
Oh, I did have a question for you though. Like, because you said, we're constrained in the upper right quadrant, the positive. Did I miss, like, what is the reasoning behind why that quadrant? I think I might have an idea, but I'd like to hear why that quadrant, not the other one.
It's arbitrary in that if you were to invert this graph, everything that's positive could be negative with no consequence. So I picked the upper right-hand corner. Well, first of all, what I'm trying to get at is I don't want to use dimension out. This is very confusing. So if I say length is a dimension, I don't believe that. It's really a direction, okay? But in common parlance, length is a dimension, height is a dimension, width is a dimension. But if you are combining not a wave form on one length or one direction with it transiting a second direction, If you combine three, it gets stuck. So once you have three waveforms all combined, you can maintain that, but they all have to stay in the same quadrant. So you could do this along, meaning you could have another three contained that are along positive length, negative height, positive width, which is the lower right-hand quadrant, right? So you could have three things all combined in the lower right-hand quadrant, or three things in the lower left-hand quadrant, or three things in the upper left-hand quadrant, or three things in the upper right-hand quadrant. So it's completely arbitrary. My point is, once you combine three directions as a simultaneous waveform, so take electromagnetism as a concept. So electromagnetism propagates along, let's say, length, but it has two additional components. One is the electrical component, one is the magnetic component, and these are orthogonal to each other, or offset by 90 degrees, but they're in phase. And so if you were to graph these things, you can graph the oscillations. And what I'm getting at is, we think it's a single oscillation, meaning we're just measuring, let's say, along length, you're just measuring height. What I'm saying is we're measuring, so let me give a better example, like a sine wave. Okay, have you ever seen an oscilloscope and there's a sine wave that propagates?
Sure.
Okay, so you have a sine wave propagating and it looks flat, it looks two-dimensional. But what if what you're looking at is, let's say, the midline of the sine wave, everything above that midline, let's just say, is graphing positive height. Below that midline, bend it towards you 90 degrees. So it looks like an L shape or a shelf. Now imagine you have two waves propagating simultaneously, one going along positive height and negative height along length, the other one propagating along positive width and negative width along length. But what you are observing is the upper half of the sine wave is propagating the positive height, and then when it dips into the negative height, what you're really seeing is the positive width kick in. So you have two waveforms that are propagating along a single direction of length, but you're only visualizing the positive aspect of each waveform, positive height, and then it transitions to positive width. But we flatten it onto a screen, so it looks like it's just height going along length.
Wow.
That makes sense? Okay.
Yeah. So it's basically, you're looking at a three-dimensional oscilloscope,
Yes.
but that's
And you
just
use-
not for,
but you're
I
using
mean,
a-
and technically for convenience, you don't need to picture that sine wave in, three dimensions, because you just know the assumption that the amplitude is always the same.
Yes, and it's always the same, you're right. And it's, in this example, there's out of phase. So the height and negative height is propagating out of phase from the width and negative width, but you're only observing the positive side of each of these oscillations, so that you're combining two waveforms along one direction of length, but you're only seeing the positive of each one. So you lose half. So you're only seeing the positive waveform of height. When it goes negative, it's like it disappears, but then positive width kicks in. And so you see the positive width. And then when that comes out, it disappears. So what you're tricked into seeing is one waveform oscillating as a sine wave above and below length.
Wow.
But what I'm getting at is combining a separate waveform, but we are trapped, as it were, metaphorically speaking, into positive width, positive height along positive length. And we're unable to visualize these other quadrants, or it's like a graph. So we're unable to bridge into the other quadrants in the graph, being trapped as we are in this massive state. Whereas something like electromagnetism Wasn't going to go here, but now we're going to extend a little bit. So let me go here. So let me ask you, Tucker. If I took an X-ray, which is a photon of a certain wavelength, and I were to shoot a photon of a certain wavelength, and you put your hand in the way, would that photon go through your hand?
It would go through parts. It would go through the fleshy parts and bounce back off the skeleton, if I'm correct.
Fair enough. Let's just say a piece of wood. Would it go through a piece of wood?
No, it would reflect off of that. No. I'm thinking of X-rays wrong. Yes, it would go through the piece of
Let's just say
wood.
jello. Let's just say jello. I mean, something super.
Yeah, it's going to
super-
penetrate through it.
Okay. And if we put a piece of film on the other side of not the bones, because that's the point of the X-rays, to find the bones, obviously, but we're just going to go through the fleshy part. We put undeveloped film on the other side. That photon goes through your tissue and it exposes the film on the other side. We agree?
Yes.
Yeah.
Now imagine you have a lead apron. Say the lead apron is 1/4 inch thick. And you lay the lead apron now, instead of your flesh, over that piece of film, and you shoot X-rays at it, which are photons. What happens to that piece of film? Does it get exposed?
No.
No.
Okay. Now take a magnet, put it over the lead apron, and put a piece of iron on the other side or another magnet. What do you think happens?
I know you told me this, but I can't remember.
I'll tell the
I'm
backstory after.
I'm guessing it's going to generate heat somehow.
It's as if it's not even there. It's as if it's air.
Which thing? Isn't there the?
The
'Cause you
lead.
said magnet.
The lead does not do anything to stop magnetism. In fact, gentlemen, nothing stops magnetism. There's only one way to obscure magnetism, the effect of magnetism, and that's with a Faraday cage. So if you can wick away the force field of electromagnetism, you could, meaning if you built a Faraday cage around a magnet, you could obscure its ability to connect to another magnet. But you can't put any insulator, you can't put any barrier, you can't put anything in between two magnets and block their effect from one another, other than a Faraday cage, which is essentially copper wires, something that will interact and remove the force, or transit the force, excuse me, and redirect it like a sponge. So no signals will get through that Faraday cage, including magnetic. But anything like a lead barrier is as if it were air. And I'll tell you, gentlemen, so my wife's a veterinarian, and we had a veterinary clinic. And when I first started discovering electromagnetism and magnetics in general, I came upon this fact, and I had to test it for myself. And I literally grabbed lead aprons, took them to a place where I had these magnets, and I tested it physically, personally, myself. I was incredulous. I didn't believe it was true, because it could not wrap my mind around how do you pass a signal, electromagnetic signal, which should be blocked by a lead barrier, which blocks very
Photons.
energetic photons. Yeah, exactly.
Yeah.
And it was as if nothing was there. It was as if it was a piece of paper. And so this is the genesis of my beginning to interpret and reinterpret and try to understand what is actually going on here. So back to the graph. My conjecture is we are looking at a physical barrier in the length, width, height quadrant. But electromagnetism is a force that is generated that breaches into the negative width, positive height, positive length, or negative width, negative height, positive length quadrants. So it's able to circumnavigate any physical barrier.
You said negative length in that, right?
I apologize. I should have said, I did it in proper order. So along positive length, negative height, negative width would be the lower left-hand corner.
Right.
And then it can also go in the lower right-hand corner. My point is the signal, the connection between an electromagnetic field and another electromagnetic field, because what it's doing when it touches iron is it's inducing a magnetic effect in the piece of iron. And these two are connecting on a quadrant that is outside positive height, positive width, and positive length. And there's no barrier that can stop this thing. So it's got an extra. Go ahead.
Sorry, because maybe I'm jumping ahead, but we're still positive length at this point. Is there something that can transcend into the negative length space?
Let's go there. Let's do this thing. Let's do this thing. Okay.
Wait, let me go drink a beer. No. Anyway.
But let me go here with let me drop the three main laws. So these are Davidson's three laws. Okay. But everything else is Newton and Einstein and all the rest. Davidson's got three. Okay. First one is the super smash. Second one is we're in a bound vacuum. Third one is everything's a wave. So to your point, John, super smash as compared to the Big Bang. So the Big Bang is something from nothing, infinitely small, infinitely dense, controlling the entire universe at time zero, a point. And from this, perhaps a quantum fluctuation, everything is generated. And there's an inflation period where the universe is expanding more rapidly than the speed of light, and all these specialized effects that theoretical physicists conject is based on an inflaton field. So there's a period of time where the universe was expanding so rapidly, and it was like a one-time thing based on this one-time field, this inflaton field. And what I'm saying is, instead of something from nothing, breaking all other known laws, and by the way, this is the first visible part of the universe by science standards today is about 300 to 400,000 years after the Big Bang, where they say we can now have visible evidence of the universe. But they have to go backwards an extra, let's say 350,000 years. They have to go backwards an extra 350,000 years to get to that first moment of the Big Bang. And they have all this area that they can't account for because it's not visible, doesn't exist. What I'm saying is super smash. Two waveforms, let's just say, are propagating in a pre-universal state. And that's a whole separate topic I can't get into right now. But let's just say there's a medium by which the waves propagate through. This is a function of waves, by the way. You have to have a medium that the wave propagates through. The wave, like say an ocean wave, the waves are going up and down, and they hit the shore. That piece of, that atom of the wave in the middle of the ocean, atom of water, excuse me, is not actually moving that far, that fast. It's not coming to you. But the wave energy it generates propagates forward and back and all around. So each atom is essentially moving up and down, or molecule of water is moving up and down. And it might slowly creep forward or back or whatever. But what's really moving is the energy of the waveform itself. That's what's propagating. That's what you see when you're on the beach. What I'm saying is, imagine there's a universal water background, medium of transfer. And instead of a singular point for no rhyme or reason, infinitely dense, all the energy in the universe suddenly springs to life and then inflates and then stops inflating, and then we start seeing the universe. What if there were two things that hit each other, like two waveforms in the proto-universe, before our universe, and when they smash into each other, they create all that we have today? So waves have a very interesting property, is that they can pass through each other, they can cancel each other, or they can enhance each other. So you can have a refraction pattern where waves are canceling each other out if they're opposing and they hit each other at the right place and time, or they can pass through each other where the oscillations are both transiting to the zero line simultaneously in opposite directions, or they can enhance each other where they're both hitting peaks together and the peaks are making bigger peaks, and troughs are making bigger troughs.
Mm.
So what I'm saying is, and this is complicated, guys, in that there's a simplicity in the Big Bang where you do not have to presuppose anything before the Big Bang. And so I think it's a cheat, but Occam's razor, it does make it more simple. My conjecture is there are two things that existed before anything that we know of. Two waveforms that were on the right path at the right time in the right phase, that when they connected, they essentially exploded. So super. And so back to your point, John, what is on the negative length? My conjecture is equal and opposite. It's all symmetrical. So just like plucking the guitar string, you have a negative length that we cannot go to, but that is the other side of the universe, meaning I believe there are two universes going on simultaneously, not overlaying. They're going in opposite lengths, opposite directions, so to speak. And we'll get into that because it does go into the three body solution. But what I'm getting at is there's a antimatter side and a matter side. Now, this is not conjecture. We all know there's antimatter. What happens when you take, Tucker, what happens when you take matter and antimatter and you put it together?
You create energy.
It creates energy. It unwinds itself. It flattens out from the loop to a straight line of energy. And so my conjecture is we have two universes going on simultaneously from a super smash, not a big bang. We're on one side of the blocks. The other universe, let's call it the negative length universe, is on the other side of the blocks. They're the 4 blocks behind the 4 blocks we can see. And their time is spinning counterclockwise, so to speak, and ours is spinning clockwise.
Oh my God. Oh my God. Dude,
I ask you, gentlemen, I ask you, knowing what you know, common knowledge of Big Bang Theory and how the universe is and exists and dimensionality, what, other than that it takes two things to create one, what seems more likely to you? That there's this infinitely small area that creates everything we know from nothing, from no impetus, for no reason, in nowhere, at no time. And then it expands in this unnatural way, breaking the laws of physics for a period of time, then it stops. Or we presuppose there were two waveforms. By the way, the two waveforms, we want to know, why does our universe have the properties it does? I think it's a function of the amount of energy in each waveform. So it's not just one wave, it's like a gravitational wave, and it's going to be a ripple. And how much energy is in that ripple and how much energy is in the other ripple as they merge together dictates the physical laws of our universe. The tension.
Wow. Dude. I was joking when I said, if you're driving, but seriously, dude, this is just so mind blowing to me. I feel like I got to share a few things, but yeah, big disclaimer on this one. Just and there's like 3 more parts, you guys, of yours. So maybe we can squeeze it in.
Started.
Well, I know it just. I got to say this. I mentioned this show Constellation. Was on Apple TV, dude. It's like these people were reading your mind, Bob. There's a line where, because it's more of like 2 realities. I think I should say, like, it's not real clear yet. There's only been 1 season, and I'm sure they'll kind of be more concrete about what's going on if they do future seasons. But so far it seems like it's just 2 realities, not infinite realities. It's 2 realities. So when you said the negative length, I'm like, check. That's what this show's about. But the thing that one of the things that really, really blew my mind, and I think you really like this, is this one character ends up he swaps with himself. So the one you see most of the time, he ends up in this negative length universe, and he knows that he's in this negative length universe, and he tells these people to take a blood sample, and he's like, if I'm right. Check this out. I think you really like this. He's like, if I'm right, my DNA is going to be rotating in the opposite direction of who you think I am. The guy he swapped places with. Now they say,
the chirality of it is exactly it.
Yeah, and some spoilers here. I should have said spoiler, but They end up saying like, no, that's not what's going on. But I, it's like FBI people that are saying it. Maybe they're just like saying, I don't know. It's very deep. It's very deep. But wow, the connections in my head, man, when you explained it that way, that's what the other thing I wanted to share, man. Yeah, a year or so ago, whenever we started chatting, you went through some of these thought experiments with me, but I don't think it at this like length, or it just didn't quite hit. I'm just sitting here just like speechless, going, I have things to do today. How am I going to do this? Like my brain is just like going to be so consumed with like just awe, just pure like wonderment, and just wow, well done, dude. Like, yeah, I
Appreciate
love
it.
this
Thank
stuff. I can't like, dude, it's so I wonder if by the way, that was I had to get some stuff out. Tucker, I want to yield to you if you have anything you want to say. 30
Ooh,
minutes. I don't
boy.
think we're gonna get through. Maybe you can tease the part two, Bob. But yeah, Tucker, what do you have to?
So the where I always end up with this is whether you had an infinite one thing that became everything, or you have the super smash where you had two things that interact and create that waveform. Where were those?
Yeah, this is the Occam's razor
Yeah.
problem. Is
Mm.
that I've
Yeah.
created more complexity in the beginning by
Sure.
adding two things. But guys, let me give it a really great analogy. And thank you, Tucker, for pushing back.
Well, hold on real
Okay.
quick though, and I guess to expound on where my mind goes then. So what if those two things are just single photons in a much larger universe? I mean,
100%.
can we
100%.
take
Yeah.
this infinitely up and infinitely down?
Suppositionally. Suppositionally with no evidence. Now I'm already supposing two becomes one and one is half of one and half of another one, meaning we're in half of the one. Negative length is the other half. So two becomes one. But to your point, yeah, it could expand indefinitely, and it's fractal. I agree, and I think what we think of as the universe is so tiny, is so insignificantly small compared to the reality of what is out there and what is beyond what we can conceive and know of. And here's my analogy. It's like you're in a jar and you figure out you're in a jar. But what you really want to do is read the label on the outside of the jar. That's hard to do.
Yep.
Yeah.
So really what you have to do is suppose some things, because you're never going to get outside of the jar. But what you could do, theoretically, let's go there. We might as well use up this time what we have on dimensionality. Let's say we want to go there, but we can't get there. Well, we can make a jar inside the jar that's fractally the same as the bigger jar that we're inside of, and look at the label on that.
Mm.
And I propose in this analogy that black holes are the jar inside the jar. And so let's go back to the three things I said. The big super smash, the universe is a bound vacuum, and everything's a wave. So the second point, the universe is a bound vacuum. The string that we described, it propagates signal as a function of the tension on the string. And it does so equally and oppositely. Well, we have a universal vibrational speed. It's called the speed of light. What I'm saying is the speed of light is a function of the tension of this string that exists within the bound vacuum. And the boundness is what creates tension, because if you had a string lying on the floor and you wanted to cut it, you could cut it. And if it were infinitely long, you would just have one cut, and you'd have, left side and right side. But if you have a bound vacuum where you actually have tension on that string and you cut it, you have an endpoint on each end. And that's what I'm inferring, is that there is an endpoint on each end of these strings. They're not tiny little strings that have tiny, tiny little dimensions. And it's not quite higher dimensions, but that is sort of a thing, in that you can punch holes through dimensionality via, say, black holes, where you're combining so much mass and energy into a single area that it's warping that space-time. So you're getting access to information from, say, a higher level, like a holographic projection, but it's holographically in 3 dimensions instead of 3 holographically into 2. Or a hypersphere is probably the better concept here, where in the hypersphere you have a sphere within a sphere, and if you exist on the boundary between the inner sphere and the outer sphere, that's more closely to what I envision. And
Wow.
a black hole is punching a hole through that. So I'm envisioning that the black hole is not a singularity, just like the universe didn't start with the Big Bang. The black hole is a bound vacuum. So inside the black hole is nothing. It's space. It's a vacuum. But outside, or what we see at the event horizon, is not just a place where the curvature of space-time prohibits light from escaping. It's an edge. It's a shell. And if you want to calculate entropy on a black hole, you do it through surface area of the event horizon of the outside. So there's a lot that, so we don't take into account the volume of a black hole when you calculate the entropy of a black hole. It's a function of its surface area. So what I'm saying is there's something there on the outside that we perceive as nothingness, so we think we can transit inside this thing. And if you take a close approximation, like a neutron star, I don't have the study in front of me, but there was something I looked up recently where light passing through a star is variable polarity. So there's no polarization, no single polarization. The waves of the photons coming through the star itself is scattered in many, many directions. But scientists figured that, hey, if we measure the polarity of the light coming off of a neutron star, we might have an understanding of what the edge or the material of the neutron star is made of. And they're right. Such that the polarity was unified. And the way they think that polarity becomes, so polarity meaning it's oscillating, say, from 12 o'clock to 6 o'clock, and not 12 to 6 and 1 to 7 and 11 to 5 and all the rest. It's in one direction. And what they found is it's true. And the answer that they posited was there's a hard layer on the outside of a neutron star. A hard layer, like a solid. And that's what I'm talking about. You get, let's go to the thought experiment of creating a black hole. So imagine you have a neutron star and there's a certain level of mass that you can pack into a neutron star. And once it goes past a certain level for the given volume and size of the star, it will then turn into a black hole. Usually this is accomplished not through a neutron star, but through a collapsing star, or the merger of multiple massive bodies. But let's just do a thought experiment. Let's just say there's a neutron star that's right at the edge. And this is the Schwarzschild radius. If anybody wants to look it up. A radius at which, with a certain given mass, an object becomes a black hole, a non-rotating object. So Schwarzschild is not doing rotating black holes, but static black holes. So let's say you have a static neutron star and you spin it. And then let's just say from space, you're orbiting above this thing and you have a cannon that shoots cannonballs of neutrons. So like neutron star material, and you can shoot these things one at a time onto the star itself. So you have a stable neutron star spinning, and it's right at the edge of collapsing into a black hole, let's say. But as you start adding mass to it by shooting these neutron cannonballs into it, it would hit the surface and it would add mass, which would contract the surface into a more dense position, but the angular momentum is conserved, so it would have to spin faster. So just like an ice skater, when she's going into a spin, as she pulls her arms in, she goes faster. She puts her arms out, she goes slower. So every cannonball you shoot onto this thing, filled with neutrons, it's going to want to collapse further inside itself because it's more massive, but it's then going to rotate faster through the conservation of angular momentum. And what I'm saying is an oscillation begins. An oscillation begins in the sphere such that the inside of the sphere, the very center of it, begins to lose its grip on holding the center, and it wants to spin out. The outer part of the sphere wants to collapse in on itself because it's more massive. And so there's this tear or rip that happens in the center of the star as it spins faster and becomes more massive. And what ends up happening is it hollows itself out and begins oscillating. The more mass you add, the bigger the oscillations until you hit a tipping point. Let's say we're one cannonball away from making this thing turn from a neutron star into a black hole. When you shot that last cannonball into the neutron star, it would collapse on itself, and then it would expand. But at this point, my conjecture is it's going to expand essentially faster than the speed of light. So this thing's growing bigger and bigger and bigger, oscillating more and more and more. The center is hollowing out, the edge is becoming the shell. And at some point, you have this giant spinning, oscillating, hollow sphere that breaks the law of physics of the tension on the string, meaning the speed of light. And it's not able to do that. And then you get this holographic representation where it disappears from our view. It becomes as a circle looking at another circle on a piece of paper. It becomes a line to us. And you lose this layer of dimensionality. It's still there. It's got the mass, but its size is smaller than all the mass could fit. Not true. It's gone into a more spacious space. It's gone into additional dimensionality. In fact, it has created another up and down. So dimensionally speaking, there's now an inside of the star and an outside of the star that never existed before. So it's adding a loop to itself. It's become a hypersphere. And we're now visualizing this boundary layer between the inner sphere and the outer sphere of a hypersphere. And its speed and rotation and mass violate the speed of light at the moment of its creation. So nothing violates the speed of light. It can't be done because there's only so much tension on these strings. So it has to then pouch into additional dimensionality, or like the quadrants, you have to make more quadrants. So it's becoming into a place that you can't visualize anymore. And in my opinion, you can't go in it. The only way to go in it is to be in a black hole yourself. If you're in a black hole state, you can combine with another black hole, but nothing goes in the black hole. It creates so much tidal forces and so much disruption. It breaks any matter into energy, and it absorbs the energy. So we talked about electromagnetism can bridge the quadrants and go from one to the other, whereas things that are bound along positive length, positive height, and positive width cannot. That's what's occurring. So energy can be absorbed by the black hole, or another black hole can merge with a black hole, but you ain't never getting inside. You cannot go inside. It's like trying to get in from the outside of our universe, which is a bound vacuum. So I'm making this a fractal representation of our universe. So this is the jar inside the jar. So we are then inside this bigger black hole, so to speak, a bigger jar that has additional dimensionality that is not so easy to find. Flip side is it's very easy to find. And that goes in another side rabbit hole, which is a solution to the Fermi paradox, is that this is very, very simple to figure out. We've overcomplicated it. And we're missing our nose to spite our face, to mix a metaphor. And the reality is, the reason why we don't see a bunch of alien intelligent civilizations out there, because this thing is so gosh darn easy to figure out. And I mean easy in that you don't need super colliders. and you don't need particle physics, and you don't need giant radio telescopes and billions of dollars of research. It can be done very simply through basic mathematics, essentially, and very simple stuff.
Well,
Not
that
to say
sounds
what,
like. Oh, go ahead.
not to say what Newton did and Einstein did is simple. I'm not trying to say that, but what I'm trying to say is what they accomplished, they did without the high tech. And so all of our breakthroughs, okay, I mean, I guess a telescope is a high tech to people who've never had telescopes. So Galileo looking at the moons of Jupiter, that's a breakthrough. But anybody could do that. I mean, it's not that hard in the big scheme of things. So things like Galileo and Kepler and Newton and Einstein and Maxwell's equations are very important. These guys, they didn't have to use trillion-dollar equipment. They figured it out. And what I'm saying is the solution to the Fermi paradox is this solution is so easy and self-evident, number one. And number two, once you apply the solution, you disappear, in that you can form a black hole around yourself or around your civilization and then go inside the hypersphere. So once you have intelligence, it becomes invisible to those who are left behind. Should I not have gone there, John? I apologize.
That was the sound of my brain exploding, by the way. No, it's beautiful. I feel like it's like a perfect place to sort of, try to wrap up, like, because part of my, like, how on earth could this be easy? Tune in next time. Oh, it's great. You know what I mean?
Easy in that it doesn't take tech. I'm saying it's not about technology. It's not about instrumentation. Not saying you cannot gain lots of insight that way, but that's not how the breakthroughs come. The breakthroughs comes like string theory. A guy just said, you know what? I wonder what would happen if we increased the dimensional variable in this equation. It was just nothing. It was just like, listen, what if? What if we do this thing? I'm just going to put it on paper. Oh, guess what? The answers work now. That's what if. So a lot of this stuff is math-based. It's a priori. It has no function from an observation of reality. It's thought experiments. It goes back to Newton and Einstein. Anyway, I will open up. I say 10 minutes left. Do we have any other points, questions, concerns?
Well, I will just plug real quick. There's a documentary on Netflix called Black Holes, The Edge of All We Know. It's great. There's a lot of stuff about Stephen Hawking's like last bits of work before he passed away is kind of highlighted in the show. And I don't think it's the exact same thing when you were talking about kind of the edges of like literally the reason it's called The Edge of All We Know is that they're talking about that that kind of edge on the event horizon and stuff. And it was really fascinating. I fully admit I wasn't completely following everything. It's presented in a way that it seems easy to understand, but retention for me, like I can't tell you everything that was in it. I'd have to rewatch it. But would highly recommend that.
Hawking radiation is an important part of this. So the evaporation of a black hole is part of this concept of everything's a wave and everything tends towards entropy. So we have this dissolution of constructive signal into this heat death, so to speak, where everything it's all a vibration on these strings. And once you end up with heat, you cannot use the energy of the vibration of the string anymore. So our vibrational energy is our temperature. And black holes are very, very cold. And so they radiate very slowly. And once they radiate out through Hawking radiation, there's a big question about the content of the information that went into them. Can you get it back out? So there's a paradox there, in that we have conservation of information in the universe. You should be able to constitute what went in by what comes out. And part of this then dovetails back into this, bound vacuum in strings and how the strings convey these signals out through ultimately heat is the very final vibration level of the string. And it's hard. It's like when the note is dying out, right? The note is dying out on the guitar. You pluck it goes for a long time, but eventually that note fades.
Yeah.
And so there's 2 points to that. One is Hawking radiation, and the other is quantum field energy. So there's energy like the Casimir effect, where you can uncover energy from the quantum foam itself. And my conjecture is that quantum field energy, this little bubbling of particles and antiparticles, and energy pops up out of nowhere from nothing. And this spawns the concept of the Big Bang. What I think is really happening is it's like a remainder. So imagine each wave. It goes up from a 0 point to a peak, then down through 0 to a trough, and back and back and back over and over again. It has to be one complete loop. You can't like do a partial loop on the wave. It's got to be a complete loop. But as the wave dissipates, there's like a remainder of the wave. And as the tension is being pulled, stretched, pushed, gravitational waves are contracting and expanding our space-time, our fabric of space-time as we speak. All these little remainders of waves kind of meet each other randomly throughout space-time, the fabric of space-time. And as they do so, they may interact. And as they interact, they may produce these little bubbles of energy, little bubbles of particles and antiparticles. And so it's a function of this global tension on the strings of the fabric of space-time.
Wow.
I don't know.
Yeah.
Like we're talking about everything as waves. It pushes me more towards right now our universe is expanding, but there's reach a point where the note dies and it instantly at the speed of light contracts back into that point and explode in another big bang polar opposite on that grid to where we were just at.
One side to the other, back and forth. That's interesting.
Yeah.
I would
Because
ask,
and it was when
where
you were
the symmetry
talking about it as a waveform. So take your three-dimensional grid, right? And you've got at the same time two bubbles forming opposite of each other. Well,
Yes.
eventually they collapse back into one bubble, which will then actually create two bubbles going out 90 degrees from your original plane.
I agree, but how do you get it started? I'm not opposed to anything you said. I think it's accurate and correct. I'm just saying, how do you get the first bubble? And I can't find it without making two bubbles first that slam into each other, and then you make this bubble, anti-bubble thing. And so I end up in this infinite regression of how do you start the game, so to speak. But I think, Tucker, you're absolutely correct. Fundamentally, it could be like that, where it's just an oscillation within the system. And maybe it's always been that way. Like, why do I have to have two things to start it? Because where did they come from? So I will grant that 100%. I'll grant that the detail lies in the original supposition of, is this a static environment that has always existed and always will exist in a series of contractions and expansions? Or were there two things that struck each other? And also, to that point, there may be other two things, and many two things all over the universe, like the bigger universe, the multi-universe, whatever you want to call it. And they could be striking each other all the time, and it could be just like a foam of universes everywhere.
Wow.
So I don't have an answer. It's like you can only read the label on your jar so clearly.
Yeah.
And once you've made a little jar that you can read the label of, maybe it's not representative of what made your jar originally. And I agree, and I grant that, and I don't have an answer for that.
Well, and that's, we've talked about this at some length in previous episodes where it's, I do believe there reaches a point where your science can't reach and it becomes philosophy. It's you can't read the outside of the jar. That's where it becomes philosophy. And because in my mind, picture in that oscillating bubble, you take that as far up and as far down as it, on every level, it points kind of to me at simulation theory.
That could
That
be
it's
too.
that
That's a
what
good
we
point.
have here has always existed and will always exist and oscillates back and forth between that because it's a piece of hardware and software working together.
Wow.
Yeah, the original is unfathomable. It's just not congruent with evidence that we have on the table. It could be literally impossible, like you're saying, because if it's a simulation, if it's a matrix, you can't determine that. You got to just take the red pill and go for the ride. I mean,
Yeah. Wow. Well, I feel like if I don't wrap it up here, I mean, we'll just talk forever.
I think we should
Which,
wrap. Yeah, I
yeah.
don't think we can continue without jumping into another rabbit hole here, obviously. And
Yeah.
it's gonna. I apologize with the parts now. I really honestly, guys, I really thought I could slam this thing in and go through it.
Nah, I love it, man. This is perfect. There's three more parts that you've outlined here. Maybe we get them all in the next episode. Maybe one episode per part. Like I'm however it turns out, I'm here for it, man. I'm so excited. This has been like one of my favorites so far. I just seriously, I have to do stuff today, and I don't know how I'm gonna not just like sit down and just be like staring off in oblivion thinking about this stuff.
I would do both. I would try to do stuff and go to daydream.
Right.
But
yeah. But not drive. Yeah.
But don't drive. Don't drink and drive. No. But I do want to throw one last little piece on here before I let go. And obviously we're gonna have some scheduling stuff in the next coming weeks, and hopefully, John, you can explain that. So it's not going to be next week technically. But I do want to give some credits and thanks. This has been really fun. I've never had the opportunity, nor have I ever had the ability, I don't think, to put these thoughts in the right order with the right people at the right places and the right times to get this information out there. So this is a one-off for me. This is the best, and it feels really good. I want to give some thanks and credit first to my wife, Stacy. She's listened to this endlessly from me for 4 years.
Yeah.
In order to
applause.
Applause. Thank you, Stacy. She's a saint, and her patience and her ability to listen so that I can go through these crazy ideas is unbound. Second is Edwin Abbott. This is the author of Flatland. I highly recommend. It's literally like a kid's book. It's not too hard. Get this book. Read this book, please. Audiobook, whatever. Mm-hmm. It will change how you visualize everything. Okay. And lastly is Dr. Jeff Weeks, and he wrote an honest to goodness textbook called The Shape of Space. And that is, it's not too hard. I believe everybody could go through this textbook. It's a math textbook, but no numbers, no formulas. It's more about this shapes. Obviously, it's called The Shape of Space. And so without Dr. Jeff Weeks' book and without Flatland and without my wife, I would just be playing with magnets.
Well said. That's great. That's awesome. So like as Bob alluded to, we're actually going to be off the next couple of weeks, just life things. But as we've been doing before, we have these call-in episodes from the call-in platform. So next week will be the final part of the series about the human evolution of consciousness. So that'll be next week, and then we'll figure out what we want to do that second week. But then, so in 3 weeks from now, we will dig back into this. It's going to be so good. Again, whether it's one episode per part or if we try to, however we do it. But again, my bet is it's going to be another one that, like, don't do this while you're driving. Carve out some time to just sit in the lotus position with your eyes closed and just really give yourself over to these kind of thought experiments and stuff. It's just wow.
Let me
so fun.
Let me just touch on the last categories. I think it's been mentioned in passing, but really quickly. So part 2 is revolved around Newton's gravity. Part 3 is Einstein's gravity, and part 4 is going to be the solution to the 3-body problem.
Beautiful. Can't wait. Awesome. Well, thank you guys so much. Thanks for listening. Get a hold of us, sendingpoets@gmail.com. Truly, thank you guys. It's been so fun. Can't wait for the next round of this. But until then, don't forget John Adams' wise words. You will never be alone with a poet in your pocket.